Hello everyone, this is 3.10, Linear Approximations and Differentials. And here the main topic, or the main, concept of this section is the following. A line that is tangent to a curve f of x can be used to approximate values of f of x when x is close to the point of tangency, which we'll call its x value a. And this is actually quite useful because basically we're going to be approximating the function by a linear function. And linear functions are a little easier to work with, especially by hand, because all you have to do is multiply and add, basically. So the main concept is the following. What I just said, but I'm going to give you a visualization here. So let's say you have this curve f, and you have a point of tangency, let's call it a. And let me just create a tangent line at that point of tangency in red. Now we're going to go by the convention of calling this line L. So in fact, it'll be L of x specifically. So it'll be its own function of x. Now, what this main concept note is really saying is that if you have an x value that is close, so what close means is kind of up to you. The closer it is, the better approximation, essentially. So if you have an x value, let's call this x, that's close to a, and again, the closer it is to a, the better for approximation purposes, what you'll notice is that if you project this up and land this on the function f and project that to the y-axis, you'll get its f value, its f of x value. Okay? And notice, if you project it to the line, you'll get its corresponding L of x value. So that's L of x, of that x value. Now what's really nice here is, again, the closer x is to a, what do you notice about these two? Well, they'll be actually less far apart, basically, as x approaches a. In other words, we can say when x is close to a, f of x is approximately L of x. So that's linear approximation. And in fact, there's a really nice way we can actually find a formula for L of x, and it's the following. L of x is equal to f prime of a times x minus a plus f of a. This is very easy to establish. Since L of x is tangent to f, its derivative is, well, its slope, I should say, is the derivative of f, which is f prime of the point of tangency, the x value of that, actually, which is a. So since its point of tangency is a, and the slope of, let me write it like this, the slope of L is f prime of a. That's just what derivative is defined as. Okay. Also, the point of tangency is, well, it's actually a comma f of a. So here f of x is close to f of a, but that's a little different. So really by point slope, we'll have y minus the y value. So that's going to be L of x minus the y value of this point. So L of x minus f of a, but I'm just adding f of a to this side, hence the plus f of a, would be equal to, so this part, the slope times x minus the x value of the point. So notice the slope is f prime of a, and then x minus the x value of the point of tangency is just a itself. So I'll let you work out the details, but I basically just said the reason why this is true. So this is going to be what we're going to be using for linear approximation. So linear approximation really says the following. So linear approximation says that, it says if x is close to a, then this implies that f of x is approximately L of x. So that's just this idea here that comes from the main concept. So I'll box these two. And we're going to use it now for this example. So here we want to approximate the square root of 4.03 using linear approximation. Now, first off, the square root of 4 is 2, so the square root of 4.03 is going to be a little bigger than 2. But we'll be actually really, really accurate. So you can compare at the end with your calculator, and it's going to be kind of fun to see what it is. But here, what f of x is going to be is just, well, the operation in question, which is square root. So it's going to be square root of x. Now a is going to be what we know that's close to the number on the inside. So the number we want to evaluate f at is 4.03, but we don't know the square root of 4.03, but we do know the square root of one number close to 4.03, and that's 4. So here a is going to be equal to 4. So that should be fairly obvious depending on the question. So in this case, I know the square root of 4.03 is close to the square root of 4, and I'm using that because we know what the square root of 4 is. It's 2. Good. So now that we have all this, well, now we want to find L of x. So for L of x, we need a few pieces. We know what a is, so we need f of a. So f of a, by the way, is just f of 4, which is, well, the square root of 4, which is 2. So f of a is 2. Good. We also need f prime of a. Well, we know f prime of x. Remember that radical x is x to the 1/2. Its derivative is 1/2 x to the negative 1/2. Or in terms of radicals, it's 1 over 2 radical x. And when we plug in x to be a, which is 4, we'll get f prime of a, which we know is really f prime of 4, is 1 over 2 times the square root of 4, which is 1 over 2 times 2, which is 1 over 4. Right, notice radical 4 is 2, 2 times 2 in the bottom is 4, so it's 1 over 4. Perfect. So we know f prime of a, we know f of a, and we just need x minus a. So from all of this, we can say the following. We can say L of x is f prime of a, which is 1/4, times x minus a is 4, plus f of a, which is 2. Good. If we distribute, then we get L of x is equal to 1/4 x. I'm going to skip a little bit. 1/4 times negative 4 is negative 1, and negative 1 plus 2 is positive 1. Perfect. So notice what I said previously. For linear approximation, all we really need to do is multiply and add. It's a lot easier than trying to figure out what the square root of 4.03 is. It's just easier to multiply 4.03 by 1/4 and then, well, then add 1 to that. So again, this is what we'll be using to approximate radical 4.03. So this L of x is approximately f of x, which by the way is the square root of x, only when x is close to 4. So when x is approximately 4. And 4.03 is approximately 4. Okay, good. So now we can say f of 4.03 then is approximately L of 4.03, which is of course 1/4 of 4.03 plus 1. A part of me really wants to do this by hand, so I'll allow you to kind of verify a few things, but I'm going to try to just run through it pretty quickly here. So I want to take 1/4 of 4.03. I know 1/4 of 4 is 1, plus, well, I'm basically splitting up 4 as 4 plus 0.03. I know the, let me see if I can say this. So I know 0.03 over 4 is kind of like 3 over 4, but the decimal place is moved twice to the left. 3 over 4 is 0.75, so moving the decimal place twice to the left will give you 0.0075. So what I'm really saying is 1/4 of 0.03 is 1.0075. So I'll allow you to verify that on your own. And then of course we have this plus 1. So altogether this is 2.0075. So that's the approximation we get using linear approximation. Now of course the only downside here really is that you have to have an a value that is close to what you're trying to approximate f at, basically. So the fact that 4.03 is close to 4, we're good. We're kind of lucky in some sense. But if we wanted to approximate, let's say, the square root of 6, well, 6 is not really super close to 4. And in fact, there's no other square root that's closer to 6 than 4 is. And their difference is kind of large if you think about, like, 0.03 is pretty small compared to 2. So in that case, you'd probably have to do a few layers, if you will, of linear approximation in order for it to actually mean anything. But here with one layer, the square root of 4.03 is going to be pretty close to what it actually is. So again, I'll leave it to you to actually verify what your calculator gives you for the square root of 4.03, but I suspect it's pretty close to this actually. So with that said, I'm going to do a few more examples, and then we're going to move into the next topic in 3.10, which is, of course, differentials. All right, so now for this example, I want to use linear approximation to estimate these three things. So, in fact, I'll be doing each three of these kind of the same way. So first off, you know what, actually, let me do this. Let me do them all simultaneously, but first we need to figure out what their functions will be. So again, the function is just the main operation, ignoring the number, replacing the number with x. So in this case, ln of x. In this case, it's going to be the cube root of x, or I guess fifth root of x, which I'll write as x to the 1/5, of course. And here f of x, of course, is going to be sine of x. There's a little bit of an issue here. The issue I'm having is that this is in degrees. We'll deal with that shortly, but right now let's just write this as sine of x. Okay, now the next thing, let me write our linearization function, L of x, right here. Remember, it's f prime of a, x minus a, plus f of a, meaning we need f, we already have f, but we also need a, which is a number close to x, that we know f of. So pick a number close to this number that you actually know ln, fifth root, and sine of. And it should be fairly obvious what they are. In this case, it's 1. So I'm going to write a is equal to 1 in this case. Here a is going to be 32, and here a is going to be 30 degrees. Again, for this one, I don't really like degrees too much. I actually prefer this to be in radians. So I'm going to recall that 30 degrees is pi over 6 radians. And I don't think that's too bad of a thing to realize, but then with that being said, x minus a, well, we'll have to deal with that when we deal with that shortly, but this will give a little bit of an issue for part 3. So they're all a little different, of course. But now we've established f and a for each of them. Also notice that we know ln of 1, 0, we know fifth root of 32 is 2, and we know sine of 30 degrees, or sine of pi over 6, is 1/2. So that's how you kind of choose a number close to what you're trying to approximate f at, but that you actually know the exact value of. Okay, so with that being said, now I'm going to develop this for each of these three, one at a time. So here, well, let's see. In fact, you know what, at this point, I'm not going to do them simultaneously anymore. I just wanted to establish that idea simultaneously. So now I'm going to, one by one, finish off each problem. So L of x, in this case, is, let's see if we can write it over here kind of nicely. So we need f prime of x. We know f prime of x is equal to 1 over x. That's the derivative of ln of x. So that means f prime of 1 is 1 over 1, which is just 1, times x minus 1, in this case, plus f of 1. We know ln of 1 is 0, so that's plus 0. So in reality, this is just L of x equals x minus 1. So I'm going to write that, x minus 1. I think that's okay, good. So with that being said, since 1 is close to 0.98, or the other way around, then from here, linear approximation tells us the following. It basically tells us that f of 0.98, which is ln of 0.98, by the way, is approximately L of 0.98 because 0.98 is close to 1, which is our a value, and L of 0.98 is easy to evaluate. It's 0.98 minus 1, which is 0.02. So that is going to be our approximation for ln of 0.98. Sorry, negative 0.02. There we go. So that's approximately ln of 0.98. And you can check that out for yourself. I believe this kind of makes sense. Yeah, that's all I'm going to say about this one. I wanted to say that it's negative makes sense because ln of e is 1, ln of 1 is 0, ln of anything less than 1 would be negative. So it's only fitting that we get a negative number. It's small because 0.98 is close to 1, so it's just barely below 0. So it's something to think about, but again, I'm done talking about that one. So on to this one. Well, we need f prime of x, and that's 1/5 x to the negative 4/5. And again, we want to develop what L of x is in this case. So we need to find f prime of 32. Now, it's going to be a little hard to write it in the space I have, but I think we're okay. So if you plug 32 into this, we get f prime of 32 is equal to 1/5 32 to the negative 4/5. Now remember, when you have a power that has a fraction, that has a denominator basically, you're really just taking the root of that number, that root. So in this case, we're taking the fifth root of 32 because the power has 5 in the denominator. So the fifth root of 32 is 2, so this is really 2 to the negative 4. Now I know 2 to the 4 is 16, right? It's 2 times 2 times 2 times 2. So 2 to the negative 4 is the reciprocal of that because negative powers mean reciprocal. So this is 1 over 5 times 1 over 16, which by the way is 1 over 80. So the slope here is going to be 1 over 80 times x minus, well, 32. Plus f of 32. F is the fifth root of x. The fifth root of 32 is 2, like we previously said. So now if we do some distribution, let me erase for space here. All right, so I made a little more space here. And of course, if we distribute 1 over 80, we of course get 1 over 80x. Let's see, then negative 32 over 80 actually reduces, what does it reduce to? Well, you can divide it by 8 top and bottom, you'll get 4 over 10. That reduces to 2 over 5. In fact, really you can just divide by 16, you get 2 over 5. Plus 2, so I'm going to write plus 2, but of course you get a common denominator. We can think of it as 2 over 1. And if we multiply top and bottom by 5, really we just get 10 over 5. Which makes sense because 10 divided by 5 is indeed 2. And notice when you combine these, you get 8 over 5 actually. So let's write that as a positive 8 over 5. Perfect. So now what we want to do is we want to say that the fifth root of 32.01 is approximately L of 32.01, which is 1 over 80 times 32.01 plus 8 over 5. You know what? Since I'm going to try to do this by hand, and I'm attempting not to use a calculator, but sometimes you kind of have no choice to, just to make things a little more smooth anyways. I'm going to write 8 over 5 as a decimal. Now I know 80 over 5 is 16 because we've already established 16 times 5 is 80. So that means 8 over 5 is going to be 1.6. And here I'm going to try to split this up kind of like I did a previous one. In fact, I'll use this for space to explain what I'm trying to do here, just to kind of show you. So I'm going to write 32.01 as 32 plus 0.01 like this. And we're dividing each of them by 80. We already divided this, we already reduced this, I think. All right, we agreed that it was if you divide by 8, 4 over 10, and that's 2 over 5. So this is the same as 2 over 5. Here, let's see, how can I establish this? Well, if you want to get rid of one of the zeros, you'd have to move the decimal over further to the left. So you end up with 0.001 over 8. Now, I know 1 over 8. I don't know what happened here. That's fine. Doesn't matter. But I know 1 over 8 is 0.125. And I know that because 1 over 8 is half of 1/4. 1/4 is 0.25. Half of 0.25 is 0.125. So it's not difficult to see that. And in fact, this looks like 1 over 8. In fact, really, this part here is just moving the decimal over 3 times to the left. So if you move the decimal 3 times to the right, you get 1 over 8. So vice versa, if you move it 3 times to the left, you get 0.001 over 8. So that means that using this idea here, moving the decimal 3 places to the left, will give us 0.000125. Now again, 2 over 5, what's 2 over 5? Well, I know 20 over 5 is 4, 2 over 5 then would be 0.4. So now when you combine these, you get a result 0.400125. Perfect. So that's exactly what this whole thing here is. So that means if you add these two, 1.6 plus 0.400125 will end up giving us a total approximation of, well, 1.6 plus 0.4 is 2, so this is going to total to 2.00125. And that makes a lot of sense because, again, the fifth root of 32 is 2. The fifth root of something a little bit bigger than 32 will be a little bit bigger than 2. And this is clearly a little bit bigger than 2. So this is our end approximation using linear approximation for the fifth root of 32.01. Great. Now back to this one. This is the one I said we kind of have to think a little bit about because it's in degrees, and the reason why that's troublesome is because if you consider the linear approximation function, x minus a, well, it's not mathematical to use degrees and multiplying degrees. I mean, we can think of x as being 31 degrees and a as being 30 degrees, and their difference is 1 degree. So this will be 1 degree. But what would it mean to multiply 1 degree to whatever f prime of a is? It sounds kind of silly already. So with that being said, radians are more, I guess, mathematical in nature in the sense that you can multiply things that are in radians because they just represent, I guess, pure units in some sense. There's like kind of unit free. So with that being said, radians are really what we kind of sought out for when it comes to these types of problems. So degrees, that's more of an applicable kind of thing. So we prefer radians when actually playing with mathematical operations. But I'm going on a little bit of a tangent. Anyways, so f prime of x in this case is just cosine. Good. So that means f prime of a, which is f prime of pi over 6, of course, is cosine of pi over 6, which is radical 30 over 2. Okay. And now what? Well, now I think we have all the pieces. Well, we need f of a. So we need f of pi over 6. We already said what that was earlier. F is 30. F is a sine, so this is sine of pi over 6, which is 1 over 2. Good. I just remember these values from the unit circle. And now I think we're set. So I'm going to erase this and then actually write the linear approximation function for this. All right, so our linearization function here is L of x equals, let's see if we can do it, f prime of a, which is this guy, radical 3 over 2, times x minus a. A is pi over 6. Again, we're dealing with things in radians now because we prefer that from what I've established previously. F of a is f of pi over 6, which is 1/2. Perfect. So I think we're set. Now what we're going to say finally is a sine of 31 degrees. Well, we have to figure out what 31 degrees is in terms of radians. Now remember, how you convert something into radians is by multiplying by pi and dividing by 180 degrees. So this is really going to be, well, yeah, this is equal to sine of 31 degrees in radians, which is 31 pi over 180. Is really what that amounts to. Okay, good. And in fact, one way of thinking of it is since A really is 30 degrees, the difference between 31 and 30 is 1 degree, and 1 degree translates to pi over 180. But we'll see that actually happen shortly. So we want to approximate this with L of x, so L of 31 pi over 180. Good. And according to our expression for L above here, this is equal to the square root of 32 times 31 pi over 180 minus pi over 6. Leave a little bit of space just to show something. And then plus 1/2 finally. So I left space because, of course, if we get a common denominator and multiply top and bottom by 30, we get exactly what I established previously. Well, what I said in words anyways. 31 pi minus 30 pi is 1 pi over the common denominator 180. So it's no coincidence that that part just amounts to pi over 180 because that just corresponds to 1 degree, which is indeed the difference between 30 and 31 degrees. So finally we end up with this in the end. And if we want to find a common denominator, I guess we can. But remember, we kind of are trying to use, I guess, we're basically trying to stay away from the calculator. So I want to use knowledge of these things to figure this out on our own. It's really difficult though because the numbers are kind of large and they're really wacky. Like I know radical 3 over 2 is about 0.866 off memory. And I know pi is obviously 3.14. And I remember 5 digits, so I know it's 3.14159. But then dividing that by 180, that gets a little involved. So just to make it short, I did this already obviously. And this is about 0.515 if you round to 3 decimal places. If you were to just go by what your calculator gives you for inputting this exactly, and compare that to what your calculator tells you for sine of 31 degrees, again remember your calculator has to be in degree mode for that. Otherwise we know to just input this in radians, but that's fine. Compare those two, they should be pretty close. But that's all I'm going to say for this example, and now we're going to move on to talk about differentials finally. Right, so here I say a differential is a small change in a variable and shares notation with derivatives. In fact, that's one way to see it, but there's a few different ways of talking about differentials. But the big picture really is the following. Oh, by the way, these are the notations for a differential depending on what variable you're talking about. But again, the big picture here is if you consider a curve f of x, let's say, and you know what, let me make it kind of more particular just so we can kind of view something. Let's just say it looks like that, for instance. And what I want to do is I want to take a look at the difference between x values, and I'm also going to compare this to the tangent line at a particular point. So we can call this line L if you want, kind of like we saw from linearization functions, but we're not really going to focus on that too much. Really all we're going to talk about is the difference between certain x values. So here you'd probably expect me to write a, but I'm just going to write x instead. And instead of writing a different x value over here, all I'm going to say is that the change in x values we'll call delta x. So if you want, you can think of this x value as x plus delta x. So delta x really is a small change in the variable. Okay? Good. So now, if you actually project to the y-axis, you get a few things. Because of course there are a few points for y. There's one that corresponds to the line, and there's one that corresponds to the function itself. Now I don't have room here for the labeling on the y-axis, but that's okay. I'm going to actually look over here. So there's actually, well, we know this distance is delta x, that's fine. This distance here, we're going to call that delta y. So that's the change between our y values, the y value of what x corresponds to, and the y value what x plus delta x corresponds to. Okay? So this is the change between those y values. Just like here, this horizontal change is the change between the x values. Now, the big picture from this image really is the following. If you look at this larger triangle, and you consider the change in y values of the larger triangle and the change in x values of the larger triangle, really what we have is the slope of the line L. Now, since L is a tangent line in particular, we know the slope of the tangent line is the derivative of f, and we have notation dy over dx. So dy over dx is going to be our slope of the line. So if we actually legitimately think of this as a fraction, as rise over run, then dy is the rise and dx is the run. Namely here, this entire difference of this larger triangle, I know it's kind of large, I know it's kind of a small picture, but just kind of let me readjust a little bit. So this will be dy, and we'll treat this as dx. And there are a few things that kind of happen from this realization. So the first thing is that dx and delta x are kind of the same. So from this idea, we get that dx is equal to delta x. So we treat those as being the same. They're just changing x's. That's fine. The next thing we get is that, well, let's see. So dy dx, remember that's just f prime of x. So that's what m is really. And if we multiply dx to the other side, then we get dy is equal to f prime of x times dx. And I think that's where I kind of want to stop this discussion, and then from here we'll take a look at a particular application and actually find delta y and dy values for a particular function. But right now I think this is okay. But this result here is basically the big result for differentials. That's kind of what a differential is. So in this case, dy is just the derivative of f times dx, and dx is taken to be just some small change in the x variable, which would be the same as delta x actually. Okay. So with that said, let's move on here. So let's compare delta y and dy values for this as x changes from this value to that value. So what we're going to do is we're going to do the following. We're going to say that x in our case is going to be equal to 2, and delta x is the change in x values, which is the difference between these two values, which is 0.01. And also we know that's the same as dx from our previous discussion. Good. Now what delta y is, it's literally the change in y values. So delta y is literally the difference between plugging these values into f. So this is f of 2.01 minus f of 2. And you can kind of see that in the image here. If you treat this as 2 and this is 2.01, then if you project them up here, you literally get f of 2.01 minus f of 2. So it's nice to have the visualization in the back of our minds. But now this becomes a little kind of tedious because you have to plug in 2.01 into this and then plug in 2 into that. So I'll do this later. So I'm just going to leave a blank space here. I'll use my calculator to figure out what this is, and I'll leave you to try to follow that in the meantime that I do this one. So I'm going to do this one live here. So f of 2 is going to be, let's see, it's going to be 2 cubed, that's 8, plus 2 squared is 4. So far we have 8 plus 4, which is 12. And then 2 times 2 here is 4. So these kind of cancel out really. So 4 squared, 2 squared minus 2 times 2, it's 4 minus 4, they cancel. So really we just have 8, which is 2 cubed again, plus 1. I kind of said that crazy, but anyways, we get minus 9. Now let's actually see what this is. The result, by the way, should be pretty small. So anyways, I'm going to use the calculator right now to figure out what this is. You could try to do it by hand, but it's not really worth it. So let's take a look to see what the calculator gives us. All right, so my calculator gave me 9.14071. 701, sorry. So that being said, if you subtract these, it just loses the 9 in front really, and you get 0.14071. And like I said, it should be kind of small. So this is our delta y value. So let me just box this and label it as delta, not delta y, not dy, delta y. Good, delta y. So we're asked to compare these two. So now we need to find dy. dy is going to be a little easier to find because we have this. So dy, on the other hand, is f prime of x. X is 2, so it's f prime of 2 times, well, dx. We know dx is equal to delta x, which is just, well, 0.01. I'll leave it like that, though, right now. So now f prime of 2, well, let me do that in red over here. F prime, the derivative of f of x, is, well, let's see, it's 3x squared plus 2x minus 2. And with that said, when you plug 2 in for x, we can do this in our heads, I think. We get, let's see, 2 squared is 4 times 3 is 12, plus 2 times 2 is 4, minus 2. Good. So we end up getting 12 plus 4, which is 16, minus 2 is 14. Let me just double check real quick if that makes sense. Yep, good. So we get 14, and we know dx is the same as delta x, which is the same as 0.01. Now, if you multiply 14 by, well, 1, you get 14. If you multiply 14 by 0.1, you get 1.4. If you multiply 14 by 0.01, you get 0.14. Nice. So this is dy. Now, if we compare these values, notice they're pretty close. In fact, this is kind of a way of using kind of a different language, I guess, to really approximate things, because dy is going to be close to delta y. So in fact, we could actually do linear approximation, but now in the language of differentials. So I'll do one example of that. And in fact, it's a little weird because we have to get used to this language of differentials. And with that being said, well, we'll kind of develop a new linearization formula, basically. Anyways, let's take a look at that right now and see what that entails. All right, so for this example, it's these two parts here. We want to estimate the following. In fact, if you want to use linearization like we discussed previously with L of x, you can certainly do that. You'll actually get the same answer, believe it or not. I'm just going to use differentials because it's kind of a more, I guess, I don't want to say mature, but it's definitely a more advanced way of thinking about it because we're using a more sophisticated language that's more calculus-based. But they're really kind of the same thing. In fact, just to give you an idea, so with linearization, we say that f of x is approximately L of x when x is close to a, because L of x is based on a. So this is with linear approximation. But in the words of differentials, basically what we're saying is if you want to evaluate f of a known value x, so this is different because here x is something we don't know f of, but here x is something we do know f of, and you add it to, well, delta x, which we know is the same as dx. This is approximately f of x plus dy. So that's kind of what we're doing here. Which, by the way, f of x is y also. So we have obviously different notation. But anyways, let's see if we can get a handle on this. So here, our f of x function is going to be y, and it's going to be 1 over x. The x value that we want to plug in is, well, the number close to this, which is 4. So in the language of differentials, x will be 4. Delta x will be the difference between what we're plugging in versus what we want to plug in. So it's actually 0.002, and we also know this is the same as dx. Perfect. Now, what's dy over dx? Well, dy over dx is just, well, the derivative of this. Now notice this is x to the negative 1, its derivative is negative x to the negative 2, or negative 1 over x squared. Now again, you probably expected me to write dy over dx, in fact I even said that, but remember we're treating this as dy equals the derivative of y multiplied by dx. Good. So now that we have that, we can find dy. So dy specifically, when x is equal to 4, and when dx is equal to 0.02, is negative 1 over 4 squared times 0.002. Which we can kind of do in our, well, maybe not in our heads, but we can definitely do it by hand. We don't actually have to use a calculator too much here. So I'm going to try to convince you of a few things. So let's see. First off, so I keep using this idea of moving decimals over, depending how many spaces you have. But first off, this is negative 1 over 16. And let me write this as times 2 times 0.001. So get that 2 out of there, that way we can cancel a little easier. So we get negative 0.001 over 8. Funny, we've seen this before. We've seen that 1/8, I convinced you of that hopefully, is 0.125. So that means 0.001 over 8 is moving this decimal over to the left 3 times because there's 3 spaces. So this is negative 0.000, moving it 3 more times to the left. And then, well, I guess from here. And then 125. Perfect. So this is dy. Great. So let me write that over here actually. So dy is equal to negative 0.000125. Fantastic. So now, what we want to find is, well, if this is f of x, what we're trying to find is f of, well, I guess 4.02, which we know is f of 4 plus 0.002. So that's what I was saying earlier, it's x plus dx. And this, according to linear approximation, basically is approximately f of 4 plus dy. Now, f of 4, I hadn't spoken about earlier, but f of 4 is just 1 over 4 because it's the original function. 1 over 4 is 0.25, so this is going to give us 0.25, but now minus 0.000125 because dy is negative that. So, I mean, there's a little bit of sorting out to do here, but here's what I'll try to do it live, but let's see. So I got 0.24, and then I guess if you think about 25 being here, we have 19, and then the difference between 100 and 125 is, I think, 875. So that should line up. In fact, I'm just going to add this to this and see if I get 0.25 and a bunch of zeros. So that plus that is 0, and then the 1 carries over, so this indeed brings a 1 over this. That brings 0, and then carry the 1 over. Yeah, okay. So I'm just checking that out in my head. Of course, you have calculators, so you can check that. But, you know, no one's ever going to need to do this by hand. It's just good to know that you can do it by hand. And that's one of the great applications of calculus. It relieves you from the calculator, basically. If you find that relieving, some people may not. But anyways, this is what I get. Which makes a lot of sense because 1 over 4 is 0.25. 1 over a larger number will be a little bit smaller than 0.25. So this is indeed a little smaller than 0.25. So again, you can compare with your calculator and see if you get approximately this. But that's what I got by calculus. So now here, this one I think will even take less time. So our y here is going to be e to the x. dy is going to be, well, its derivative, e to the x times dx. Dx, by the way, well, I guess first off we have to figure out what we're plugging in. So our x value we want to plug in this case is going to be what this is close to that we know e to that power of. And it's 0, because we know e to the 0 is 1. So that means delta x is really what? You have to be a little careful. Now delta x is really the difference between, well, this and x. Now the difference between the two, so it's kind of going backwards, but basically it's going to be, I guess you could think of it as negative 0.015. I mean, it just kind of depends, because you don't want to do, I mean, we normally do x minus this. I mean, if you look at how we did this, we did actually the opposite way. So we did what we want to plug in, or what we wanted to approximate basically, minus what we're plugging in, so kind of like our a value. Maybe I should have used a just so it doesn't sound too confusing, but I'm just using x. But anyways, we did what we're trying to plug in minus this. So if we do that here, what we're trying to plug in minus 0, it would be negative. So I think that makes sense to make it negative. And in fact, I'll kind of talk a little bit more about that once we're done. So notice this is just dx. So altogether we have dy specifically when x is 0 is e to the 0 times our dy value. Good. E to the 0 is 1, so this is just negative 0.015. So that means e to the negative 0.015 is approximately, well, e to the 0, which is y, so e to the 0, plus dy, which is negative 0.15. So really it's just this, hope you don't mind me erasing this, but it's 1 minus 0.015, which is, I guess, 0.985. Good. Now, again, if you didn't like that whole argument I was having with myself about what delta x is, if we did the subtraction the other way, then we would have got 0 minus negative this, and 0 minus a negative is positive, and you end up getting positive. Now, if that was the case, then we'd actually get 1 plus something and be bigger. Now, the argument is the following. E to the 0 is 1. E is an increasing function, so it actually looks something like that if you were to graph it. But with that being said, e of a larger number will be larger. So if you have e to the x and e to the y, and x is smaller than y, then e to the x will be smaller than e to the y. That's what increasing really means. Meaning, e to a number smaller than 0 will be smaller than whatever e to the 0 is. And this makes sense actually because notice, it's no coincidence, 0.985 is smaller than, well, 1, which is e to the 0. But again, you can check with your calculator as well to see these should be pretty close. And again, you can also try by the linearization method, and you should actually get the exact same answer, funny enough. We're just using a different language, that's all. So anyways, that's it for 3.10. That's all I want to talk about anyways. I'll see you in the next video for more of this great applications of calculus. So see you then. Thanks for watching.